Alright, so let's take a look at statistical hypotheses. Now, these allow us to determine whether there's a statistically significant difference between two groups. Now, the null hypothesis is the hypothesis that there's no difference or relationship between a disease and a risk factor. Example of this might be looking at lung cancer and smoking, and a null hypothesis would state that there is no association between lung cancer and smoking. Now, what do we know about lung cancer and smoking? Great, that there is an association. So, what would that mean? There you go, that we would be rejecting the null hypothesis here. Now, the alternative hypothesis states that there is in fact a difference or relationship between the risk factor and the disease. So, for our lung cancer example, the alternative hypothesis would state that there is an association between lung cancer and smoking. And since we know this to be true, we would be accepting our alternative hypothesis. Now, these hypotheses will show up on various statistical tests, and we'll discuss this more when we discuss outcomes of statistical hypothesis testing. All right, so now let's talk about types of errors when evaluating a statistical hypothesis. When looking at outcomes, you can end up with essentially two results. Either you're correct or you're incorrect. And if we look further at correct results, these mostly occur in two ways. The first way, you state there's an effect, a relationship between a risk factor and a disease, and you're right. The second way is you say there's no relationship, and again, you're right. Simple, right? But let's explore that more deeply using null and alternative hypotheses. So what does the null hypothesis say again? There you go. That there's no association between the disease and the risk factor. Now the alternative hypothesis that says yes, there is an association, opposite view. Let's say you review patient data and conclude, yep, lung cancer and smoking are linked, and you're right. Would you accept the null? Nope. You'd reject it and accept the alternative. Now, just like results can be correct, they can also be wrong, and that's where errors come in. We have type 1 error or alpha and type 2 error or beta. Let's break that down. A type 1 error is when you say there's an effect, but there actually isn't. That's a false positive. You rejected the null and accepted the alternative, but you were wrong. In hypothesis terms, you rejected something true. Type 1 error is marked by alpha. If you check your 2x2 table, alpha is where you find the false positives. Now here's a key stat link. The p-value of your study equals the probability of making a type 1 error. And that p-value, it's often measured against 0.05, the classic significance level. If your p-value is less than 0.05, that means there's less than a 5% chance your finding is random. That's why a lower p-value, a more confidence that your result is real. Now let's flip to the other side, type 2 error. This is when you say there's no effect, but there actually is one. You missed something real. In hypothesis terms, you fail to reject the null, even though it's false. That means you don't accept the alternative, even though it's true. Type 2 error is the false negative marked by beta in your 2x2 table. Beta is where your false negatives hide. Now beta has a counterpart, power, which is 1 minus beta. So anything that reduces beta increases power. Here's a question for you. How do we reduce type 2 error? Exactly, increase sample size. More people, more accurate reflection of the population. That reduces your chance of missing a true effect and boosts your study's power. Now, what exactly is power? It's the probability of detecting a true effect or rejecting the null when it's false. In simple terms, power tells you how good your study is. A high power study means a high chance you'll catch what's real. Mathematically, power we are 1 by data, and that corresponds to true positives in your results. Let's try a fun analogy. You're flipping a coin, null hypothesis, it's fair. Alternative, it favors heads. We flip it 10 times, 6 heads, 4 tails. Is that enough to reject the null? Not really. Power's too low. Now, flip it 1,000 times, 600 heads, 400 tails. Now you've got power, enough to reject the null and say, yep, this coin favors heads. So how do you increase power? Let's count. Increase sample size, reduce data spread, aka variability. Increase precision, increase alpha, increase effect size. Quick tip, reducing spread increases precision, and precision makes it easier to find differences, thus increasing power. Also, yes, If you're willing to increase alpha, you reduce beta. Less beta, more power. Alright, did you catch all that? Let's do a practice question. Researchers are designing a study to test if a new beta blocker reduces side effects and improves survival in MI patients compared to standard care. They want to avoid saying there's a difference when there really isn't one. Which parameter do they want to maximize? A. Alpha. B. Beta. C. 1 minus alpha. D. Power. Answer C. 1 minus alpha. They want to minimize alpha, the probability of a type 1 error, or false positive. So if you minimize alpha, you maximize 1 minus alpha. Now, beta refers to type 2 error, missing a real difference. That's not what they're worried about here. They want to avoid falsely claiming a difference. So they're focused on alpha, not beta. Maximizing power is great, but that's about catching real differences. This question, it's about avoiding false ones. So the correct answer is again C, 1 minus alpha. C.